Now we're trying to get a confidence interval for a population parameter, population proportion P. We're going to use P hat to estimate that. P hat is x over n, the number of successes divided by the total amount. And then Q hat is the complement of 1 minus P hat. So we have our familiar form. We have the point estimator on the left, the error term on the right. So the point estimator, P hat, plus or minus the critical value. We get to use the z distribution. We get to use that as long as our sample size is large enough. Our criteria for large, meaning n times P hat is 15 or more, and n times Q hat is 15 or more. According to the central limit theorem, that's large enough for P hat to be considered approximately normal, so we will use the standard normal distribution. The standard deviation of P hat equals square root of P times Q over n. Now we won't have P and thus we won't have Q because we're trying to estimate that parameter, so we'll use what we have. We'll use the point estimate for P, which is P hat, and the point estimate for Q, which is Q hat, in our ultimate confidence interval. So P hat plus or minus the critical value z of alpha over 2 multiplied by the standard deviation of P hat, which we're going to approximate to be square root of P hat times Q hat over n. So here's an example. We got a confidence interval for proportion. The information that you're given is that the sample proportion P hat is 0.11 and n is 150. So we're going to use this as our confidence interval because n times P hat is 150 times 0.11, which is 16.5. That value is greater than 15, and if we use 0.89, which is much larger than 0.11, this too will be greater than 15. So our criteria for large sample is fitting, so we will get to use a z. If we're not going to be dealing with small samples for proportions, so this is the only confidence interval formula that you need to know about for proportion. Now we're just going to fill everything in. So P hat is 0.11. For 95%, we're going to use 1.96. Inverse norm of 0.025 gives us negative 1.96, which we use 1.96. And P hat is 0.11, Q hat 0.89, and n is 150. So this comes out to be 0.11 plus or minus 0.05. So our lower bound is 0.06 or 6%. Our upper bound is 0.16 or 16%. We could use this for interpretive purposes if we were trying to determine if the true parameter was 0.2. We would have to say no because our entire confidence interval is below 0.2. Or specifically, we just look to see if 0.2 would fall within the interval as on a number line.